All right, welcome to the Explainer. Today we're diving into what is basically a crazy high-tech engineering challenge. We're going to look at how you can take one of nature's most beautiful and frankly slow-growing creations and put it on absolute fast forward. We are talking about growing coral at almost unbelievable speeds. So just imagine this for a second. What if you could take a tiny, fragile piece of coral and grow it into a huge, thriving colony at a rate that just seems impossible, maybe 50 times faster than it would ever grow in the ocean? Well, look, this isn't science fiction. For the people on the cutting edge of coral growing, this is just another day at the office.
So how do they pull this off? Well, it's definitely not magic, it's pure science. And the best way to think about it is like a recipe. Probably the most complex, most precise recipe you can possibly imagine, where every single ingredient, every single step has to be absolutely perfect. So today, we're going to break that recipe down, piece by piece.
First up, the absolute bedrock of everything, the water itself. You know, you can't build a strong house on a shaky foundation, and it's the exact same idea here. You can't grow coral without a perfect chemical bedrock to build on.
The single most important ingredient in this entire recipe is alkalinity. Think of it as the available supply of building blocks. These are the carbonate ions that the coral literally uses to build its skeleton. It's what we call a limiting factor, which means it's basically the speed limit on growth. You can have everything else perfect, but if you run out of these blocks, construction just grinds to a halt.
But what's really fascinating is how these three things work together. Calcium is the raw material, and alkalinity lets the coral use it. But magnesium is the unsung hero. It acts like a chemical referee, keeping the other two stable and available. And just look at those stability requirements. We're talking about a window of plus or minus 0.3 DKH. That's an insanely narrow target to hit 24/7. And that right there shows you why all that precision is absolutely worth it. Just by keeping that one parameter, alkalinity, elevated and rock-solid stable, growers can see growth rates jump by up to 70% compared to what you'd see on a natural reef. I mean, that is a massive, massive performance boost from just one chemical tweak. So here's the takeaway, and it's a big one. Stability is actually even more important than hitting some single perfect number. Think about it. When these parameters are swinging all over the place, the coral gets stressed out. It stops building its skeleton and puts all its energy into just trying to stay alive. But rock-solid stability, that lets the coral stay in growth mode all day, every day. All right, so we've got our chemical foundation completely locked in. What's next on the recipe card? Well, now we need the fuel. For corals, that fuel is light. It's the engine that drives this whole photosynthetic growth process. So when we talk about light for corals, we measure it in something called PAR, photosynthetically active radiation. Basically, it's just a number for how much usable energy is hitting them. And as you can see here, different corals are tuned to different light levels. The super fast-growing acropora that live at the top of a reef, they need really intense light, somewhere between 350 and 500 part to really get going. It's all about giving them exactly what they evolved to handle.
But here's where it gets really cool. It's not just about how bright the light is, it's also about the color of that light. Research has shown that a light spectrum that's really heavy on the blue light, which is what penetrates deepest in the ocean, can boost growth rates by a mind-blowing 32%. That's because the tiny algae living inside the coral are just way more efficient at using blue light to create energy.
And of course, the pros have figured out how to hack this even further. They use a strategy that copies a natural day. They'll run that powerful blue light for the full photo period, maybe 10 or 12 hours, but they only blast the really intense, full-spectrum white light for a few hours right in the middle of the day. This avoids something called photo inhibition, which is basically like a circuit breaker tripping because the coral is getting overloaded with energy. This strategy gets you maximum energy with minimum stress.
Okay, recipe check. We've got the chemical foundation, we've got the fuel. Now we need a high-speed delivery system. And that's where water flow comes in. Trust me, it's way more important than most people think.
So you might be wondering, water flow, what's the big deal? Well, it's solving a huge problem, an invisible barrier that surrounds every coral, one that can literally starve it to death, even if it's sitting in a tank full of food and building blocks. And this is it. It's called the diffusive boundary layer, or DBL for short. It's this tiny, stagnant film of water that just clings to the coral's surface. The best way to picture it is like wrapping the coral in a thin layer of plastic wrap. Food can't get in, and waste can't get out.
So how do you get rid of that plastic wrap? You blast it away with intense, turbulent, chaotic water flow.
It literally acts like a powerful scrubbing brush, ripping away that stagnant layer. When that happens, the coral can finally breathe properly, absorb all those crucial elements from the water, and flush away its waste. It's a total game changer.
All right, this next part of the recipe might actually surprise you because for decades, the common wisdom in the hobby was just plain wrong, and it all has to do with what corals actually eat.
You see, for the longest time, everyone was obsessed with creating these ultra-low nutrient systems, trying to keep the water as sterile as possible. But as we know now, that was like asking a professional athlete to compete on a diet of nothing but water. It just doesn't work. Corals are animals, and they need food to build tissue and fuel their growth.
And this is what a real, balanced diet for a coral looks like. We're not talking about dirty water, we're talking about very specific, controlled levels of nutrients. Notice how precise those targets for nitrates and phosphates are. And on top of that, you're adding things like plankton and amino acids. These are the proteins, the fats, the building blocks for healthy tissue and a dense, strong skeleton.
All right, we've nailed all the fundamentals. Now we get to the really fun stuff, the pro-level hacks. These are the little interventions and secrets that push coral growth to its absolute biological limits.
You know, one of the biggest secret weapons here is pH. And believe it or not, the CO2 from you just breathing in the room can dissolve into the tank's water, lower the pH, and slow down coral growth by as much as 25%. So by using a simple CO2 scrubber on the aquarium's air intake, growers can raise the pH back up. This just makes it way easier, energetically speaking, for the coral to build its skeleton, and it unlocks a ton of growth potential.
But here's a classic problem. What do you do when you've done everything by the book? The water's perfect, the light is dialed in, the flow is amazing, and a coral just stalls. It just stops growing, and you can't figure out why. It's super frustrating.
Well, the solution is kind of crazy. You actually have to hurt it, just a little bit. It's called clipping the tip, and it's basically giving the coral a strategic haircut. By snipping off the very end of a growing branch, you trigger this powerful healing response. The coral rushes all its resources to that spot, and that process often jump-starts the entire growth engine all over again.
So let's put it all together. Think of this as the final, master recipe card for maximum growth. You start with that rock-solid chemical infrastructure of high alkalinity and stable pH. You fuel it with optimized blue-heavy light. You deliver everything with high-energy, turbulent flow. You feed it a very specific nutrient-rich diet. And then you layer on these advanced pro strategies to break through any barriers. It's a complete system where every single piece works in harmony to create this incredible supergrowth.
And you know, all of this incredible high-tech engineering in a glass box leads us to one final, really big question. If we've gotten this good at engineering and accelerating life in a perfectly controlled environment, what can we learn from all this to help tackle the much bigger challenge of restoring our natural reefs out in the wild? It's a huge task, but this at least shows us what's biologically possible, and that's a pretty powerful place to start.